Hey everybody, thanks for joining our July version of our Clear Calcs Learn our webinar. As I'm sure you guys noticed since you signed up for it, we'll be chatting about shear walls today. It looks like we got about 41 attendees so far. Like typical, we'll just wait a minute or two in case anybody's working on meeting a deadline here and just running a minute or two late. And like always as well, if you guys want, go ahead and post, your name, job title, company, and maybe where you're tuning in from in the chat. So that way we get a better feel of our Clear Calcs community and we can kind of learn from one another and see where we're tuning in from. And then like I mentioned, maybe we'll start in about a minute or so because we are recording all of these and everybody could watch back. Thanks for sending through Aaron Wilson from Maine. There's good beer out in Maine. I haven't made my way out there, but I've had quite a few beers from out there, Portland, Maine. Hey, Tim, thanks for joining. David, good to see you. Long time no chat. And then, yeah, for the sake of time, I know everybody's kind of got work to do. And like I mentioned, appreciate you guys joining. We'll go ahead and get going here. Now, everybody who kind of joins in and they're kind of trickling in as we get going, just remember we are recording this so you can start and hear me blabber on for the first minute before Laurent actually gets into the good stuff. So kicking it off here, like I mentioned, we're gonna be chatting shear walls, how they work, and how to design them in Clear Calcs. This is one we're very excited about. We know we've had quite a few requests for wood shear walls in the past, at least since I joined a few years back. So very excited to showcase this one. And then most people that are joining, I'm assuming, are either familiar with Clear Calcs because you guys are users or at least have trialed it. Quick overview of Clear Calcs. It is a cloud-based structural calculations platform. So we aim to be more accurate, eliminating wasted time and available anywhere and everywhere. And then myself, I know I've chatted with most of you before, but I am Connor Conzelman, our Director of Customer Success. So chatted with a lot of you through demos or training sessions, even after you potentially decide to purchase. And then who we have here, the man, the myth, the legend, Laurent, who is the head of our North American engineering content. So leading our work in the US and Canada. I'm sure most of you have sent a few support emails back and forth with Laurent as well.
Hi, everyone. And so thanks a lot, Connor. Maybe I'll take it over from here. So thank you, everybody, for joining us today. I think this is a really fun webinar. Pretty excited to be doing this today. We put a lot of work into our shear wall calculator, both in terms of learning about how everyone uses it and how we can kind of best complement your day-to-day life and how you're using shear walls in practice, and then also in actually making a calculator. And it's something that we're constantly working on and we're always looking to improve. So the one thing I will say through that, at any point, please send some feedback. If you've got any ideas, send them along. We'll be taking notes here, and then we're planning to act on that. So with that said, what are we here for? So you saw the webinar, it's about shear walls. And so we'll be talking about shear walls. The first thing is, what is it? What's a shear wall? How does it work? Then a little spoiler alert, we're gonna have a little bit of a story time, a very short one, and you'll see what I mean by that. Then we're gonna look at specifically what are the components of a shear wall and how do we typically design them in America. And we're gonna finally do a worked example in Clear Calcs. So let's get started. So what do shear walls do? Basically, the easiest way to put it is they make sure your building doesn't fall sideways. In more engineering terms, they take lateral loads from the building to the ground. So that would be usually wind or earthquake loads. And they make sure that they go all the way to the foundation and that the building remains stable while that happens. Typically in North America, we'll see these being made out of wood, concrete, or masonry, sometimes a combination of all these. There are other ways to prevent a building from falling sideways. We're specifically looking at shear walls today, but you might hear about braced frames or moment frames, portal frames, things like that. Those are all other methods, but today we're looking at shear walls. So I added a picture here. This is from, I believe, the Northridge earthquake in California. You can see what happens when a shear wall goes wrong. the whole building kind of tips sideways, which obviously we don't want. We don't want, and the users of the buildings also don't want, right? So I told you about a story time. So you've probably all heard about the three little pigs. Maybe it's been a while since you heard about these. So I'll just kind of summarize the story really quickly. There's these two lazy pigs. Well, the three pigs, two of them are a little lazy. One of them builds a house out of straw. The other one builds it out of wood. And the last one builds it out of brick. Until one day, some big mean wolf comes along and he's hungry for some bacon. So he blows on the houses, the straw and the wood ones collapse immediately because the lazy pigs didn't put too much effort into it. But they managed to escape to the brick house, and the hard worker who spent days and days building his brick house saves everybody from turning into bacon, and they all have a big party in there. So the lesson here is, hey, don't be lazy. Hard work pays off. The pig who built the brick house, he was okay, didn't have to worry about the wolf. Then the lazy ones, well, they almost turn into bacon. So that's the lesson, right? That's what we've all learned when we were kids. I think, however, maybe there's another lesson here. And the real lesson is you can be lazy, but you need to have shear walls. And so look at that. We've got a shear wall here, wood shear wall. We've got our wolf, he's blowing on it. This house is not moving, and our pigs are all happy, and they get to be lazy, and they get to be safe. That's why we want shear walls, because they help prevent collapses from wind. So how do these things actually work? For a wood shear wall, there's typically going to be four main components. The sheathing, so in this case, you can see this is OSB. You could have plywood, so you could have sometimes gypsum wallboard, you could have sheathing lumber. There's different types. Today, we're mostly going to focus on OSB or plywood. That's usually the most common one we see in North America. You need nails, and you're going to use these nails to fasten your sheathing to dimensional lumber. Typically, we'll see a 2x4, 2x6, basically a stud wall, right? And you need anchors to anchor your shear wall to the ground to make sure it actually transmits the load to the ground. Now, looking at it from a more engineering side, what actually happens? So we've got lateral loads at the top, and these lateral loads go through the top plate into the sheathing, and then they go through the bottom plate, which is connected, nailed to the sheathing, and then this bottom plate is connected to the foundation with some anchor bolts, and that's how the load actually goes down to the ground. Now, on top of that, because the load's applied at the top of the wall and not kind of uniformly over everything, and it's only attached at the bottom, this whole wall assembly also kind of has a tendency to want to flip over. We call it overturning. So while the sheathing is kind of carrying the sideways loads, we also need to have what we call cords at the ends, and these are attached. You can see there's a bigger anchor here. We call these hold downs. This one's attached to the foundation, and that's what we use to prevent the entire wall from basically tipping over, overturning. Now, if we think about these components in terms of, okay, how do we actually design these? There's a couple kind of key criteria that we look at here. First of all is the sheathing. The typical thing that we'll look at is what's the thickness and what's the spacing of the nails that's attaching it to the dimensional lumber. And we'll look at what that means later on. After that, we'll look at the cords. The typical question here, because you're dealing with a stud wall, you've probably already got your stud spacing, stud size determined. But because the cords take a pretty big chunk of load to make sure that it's not flipping over, we might need more than one stud at the end of the shear wall. So that's typically the question we'll ask ourselves. Then we'll have our connections. So there's two main connections to the foundations. There's the sill or bottom plate anchors. So these are the ones that transmit the lateral shear into the foundation. And then the hold downs, these are the ones that prevent the overturning. And then we've also got connections at the top of the shear wall. That's our, call it diaphragm or floor connection to our shear wall. We're not going to talk too much about these today, but they are an essential part of shear wall design. And lastly, we also have to look at deflection. So how much does our wall actually move when it's being exposed to wind or seismic loads? So in America, there are standards, there are building codes to respect when we're designing any building, and shear walls are not an exception to this. So The typical standard that's used for engineered design is going to be the Special Design Provisions for Wind and Seismic, SDPWS, made by the American Wood Council in 2021. The previous version was 2015, which some of you might be used to see as well. The other thing as well is because we're dealing with dimensional lumber, we're often going to use the National Design Specification, the NDS, to design the lumber components of the shear wall. As with any other lumber building, you can use either allowable stress design or load resistance factor design. Both of these are completely supported by the standard. I think what we've mostly seen on our side is ASD for wood design. However, either method is just as supported by the standard. And really the only difference is at the end you divide by a different safety factor to get the different capacities. There's other options as well. The International Residential Code, or the IRC, has prescriptive requirements. These can get pretty complicated actually. So we've seen some contractors that prefer to just go straight to the engineering design and not even try to deal with the IRC. There are other cases where if you're really familiar with the IRC, you might be able to do a really quick design using those prescriptive requirements. It's another option out there. So in ClearCalcs, we focus specifically on the SDPWS. However, it's good to know that there are other options out there. Now, one big component with shear walls are openings. These probably have the biggest impact on the strength of a shear wall. If you think about it, you're basically putting a big hole in the middle of your wall, and so when things are getting pushed around, there's obviously going to be some weird things going on with the stress. It's a big weak point, so we absolutely have to consider that. And so the code usually gives you 3 different methods that you can use to design openings. The most common one, and also the most conservative, is the segmented shear wall method. So that's the one on the left here. Basically what we say here is whenever there's an opening, we just ignore whatever's above it, we ignore whatever's under it, and we just look at every panel between openings as if they were individual shear walls. So you can see at the bottom there's the H here for hold down. So every panel is going to have a hold down anchor because every panel we assume kind of behave independently. Next, we've got the perforated method and the force transfer around opening. So both of these methods, FTAO for force transfer around openings, both of these methods are basically a more accurate or more kind of complementary version of the shear wall analysis. So perforated shear walls are kind of an empirical method looking at how shear walls perform. They give you some kind of direct formula, some factors that you can use to adjust your shear wall capacity. And it means that you get to use basically the entire shear wall, which means you can use less hold downs because you're considering it as one big chunk. So you can see we've only got hold downs at the end. And then finally, the force transfer around openings is basically the big fancy version where you can do basically rational analysis, right? So you can go pretty into detail about how the shear gets transmitted around the openings. You can reinforce certain areas, and that's usually going to let you use more capacity out of your shear walls. However, that usually means you'll have some additional detailing requirements as well that you want to consider. So again, in practice, the most conservative method and the most common method is the segmented shear wall method. And as we'll see later on, that's the method that we use right now in ClearCalcs. So I talked about the different components to design. The first one is going to be the sheathing. So if we look at the SDPWS, there is table 4.3. And that's basically a big table that tells you if you've got some sheathing of this material with nail spacing of this is your linear strength that you can take with your shear wall. So just to give a bit of an example here, we've got a 7/16 structural 1 panel. So structural 1 being the higher grade of plywood, and we're using edge nails at 4 inches. So I've highlighted it in yellow here. Now we mentioned that this is a block shear wall and the aspect ratio is less than 2. The reason we mentioned this, if not every edge of the shear wall is supported by wood or fastened directly into wood, that also has a significant impact on the strength of the shear wall. And so we consider these blocked or unblocked. So blocked means every single edge of the panel is nailed into wood. Higher capacity basically means we get to use a full capacity. If it's unblocked, we have to take a pretty significant reduction in the capacity of our shear wall. Other things that we want to look at. I mentioned earlier, ASD and LRFD have different safety factors. So you can see here, we've got the 2.0, 2.8, 0.8, 0.5. And this is new in 2021, actually. In previous versions, these were separate tables for wind and seismic. Now we're actually using one nominal value and we're adjusting it separately for wind and seismic. So we can see here for ASD, we'll have a different allowable load for wind than for seismic, same with LRFD. So basically, if you have a blocked shear wall and it is relatively wide, so much wider than its height, you can basically just take the values in this table and divide them by the safety factor, the appropriate one for wind or seismic, and then just, that's it, that's your linear capacity. There's also different materials in this table. So we've got gypsum board or sheeted lumber. We're only going to look at plywood or OSB today, but these are also possibilities for design. Next, we're going to look at the cords. So I mentioned earlier, this is what we use to prevent the entire wall panel kind of flipping over, right? We've got the drawing on the bottom right here. There can be some pretty significant forces going in there, especially when we've got relatively narrow panels. These forces are basically the shear load at the top divided by the width. So for short panel, you can get really, tall panels, you can get really high forces in your cords. And typically a single stud won't be enough to carry those loads. So this is where we're going to design these as columns per the national design specification. So just like a typical column, we're using the unbraced length. Typically, because it's sheeted, we'd consider it braced in the weak axis, but we'd still design it as a column, and we'd also design it as a tension member, specifically accounting, again, if we're drilling holes for anchors or something like that, we want to take that into account because that significantly affects the tension capacity of our studs. One thing that sometimes gets forgotten is we also want to check crushing. So usually these cords will sit on the sill plate. These cords can actually be so strong that they'll crush through the sill plate, which obviously we don't want as well. And so the National Design Specification offers checks for that as well. Just like a typical column or a stud in a wall, it's just typically with higher loads than a normal stud. Next, we've got the sill anchors. So what these do is, again, we've got sideways loads. These anchors are here to make sure that the wall doesn't kind of slide off. If it was just kind of sitting there, you'd push on it, and you've pushed a box before in your life, I imagine. You can imagine that if you push on it, it's gonna move, so we need to fasten it down to the ground. Typically, we'll see these as embedded bolts. So these might be kind of 1/2-inch bolts that are about 7 inches deep in concrete. They'll typically have kind of a hooked end. And then there's different ways to calculate that. The other ways that we might see it is, for instance, Simpson strong tie will have sorts of straps that are embedded in the concrete, and these will also work to anchor our sill plate. So in terms of finding the bolt spacing that we need here, there's kind of two different approaches. Perhaps the more engineering way is to look at the National Design Specification. In there's table 12E, and that gives us the design capacity for bolts embedded in concrete fastening lumber. Interestingly, if you've designed with ACI 318, which is the concrete code, if you use the provisions for anchoring to concrete in ACI 318, you would find much, much lower capacities. The reason for that is typically there's big penalties on ductility within ACI 318. However, there has been some research that's been done on anchorage of sill plates specifically. And because of that, the International Building Code and most building codes around the United States have an exception specifically for sill plates anchored to concrete that let you use the higher capacity provided in the NDS. So you don't need to check with ACI typically, and then you'll want to check with your local regulations. But typically, you do not need to check with ACI for the anchoring to concrete provisions here. You can just go directly in table 12E and get your capacity. Alternatively, there's also the International Building Code that has prescriptive requirements. And these requirements are actually quite simple. It'll be, you need a bolt within 12 inches of the end of each piece of wood. And the spacing has to be at least 6 feet. So if you've got 8-foot boards, you'll typically have 3 anchors per board. And if you have more than 1 story, there are additional requirements that get on top of that. So 2 generic methods, basically, the NDS, which is the calculated method with actual capacities, or the IBC that has the prescriptive requirements. Finally, we've got hold down anchors. So these I mentioned are connected to the cords, and the cords take big loads. These can be, 5,000, 10,000 pounds going through the cords. A typical little bolt going to concrete might not be able to support this. And on top of that, the connection between the stud and the sill plate might not be adequate to carry that load either. So how do we deal with that? The typical method that we've seen is to use manufactured connectors. So Simpson Strong Tie is a big one. We've got 2 examples here. So you could have, they will make basically pre-engineered, mass manufactured brackets that take care of the connection from the stud to the sill plate into the concrete. So you can see on the left, we've got one for bolted connections, so basically bolting into the cords, or we can also have screwed ones and sometimes even nailed connections as well. Once these are designed, so the manufacturer will do some tests, and they'll typically kind of have some tables out there that tell you the capacity of these connections. An important thing to note, however, is that these tables will typically only look at the connection to the cords and not at the actual anchoring to concrete. So you would still need to figure out how deep your bolt needs to go into the concrete, how big the bolt needs to be. This is typically not included as part of the design specification for these brackets, so something to keep in mind. Finally, we also have deflection. So I mentioned that we have to check deflection. This is typically mandatory for any kind of building with significant seismic loads. The reason we're looking at that is that we want to make sure that during an earthquake, the building's not going to tip over so much that it starts being unstable. So for most wood buildings, we're thinking about 2%, 2.5% of story height. If you're thinking in terms of serviceability, that's really high. That's a pretty significant lien on your building. The reason for this is at the ultimate load level. So this is during the big earthquake. We don't really care if the windows break or anything like that. We just want to make sure that the building is still standing at the end. We can also check this for wind loads, although from what we have seen in the past, it's quite often ignored under wind loads. One question to ask yourself here is, obviously every project is different. So if you see some sensitivity to wind loads, so for instance, if you got some fragile finishes or some big patio door that's really sensitive to deflection, you're definitely going to want to check that under wind load as well. So when we calculate the wind load, there are 4 components usually that we'll consider for a shear wall. The first one is bending deflection. So if you think about a shear wall as a bit of a cantilever beam, so it's fixed at the ground and then just sticking out in the air. The first one is it'll bend like a beam. And the biggest way that we have to prevent that bending, just like an I-beam, is the flanges, which in this case are the cords. So the bigger the cords, the less bending action that we get. Next is the actual shear deflection. So that's our sheathing getting stretched out. And that also has an impact. So that's what makes it kind of look like a parallelogram. So we also have to look at that. We also have to think about the nail slip. So when the sheathing is fastened to the wood, there's always going to be a bit of slippage as this thing moves. So that also increases our deflection. In the SDPWS, this is already accounted for. So the design specification gives you an effective sheathing stiffness, and that already accounts for the slip in the nails. So that's why if you see the equation on the right here, it doesn't have any term for nail slip. It's only got 3 terms. And then finally, we've got the anchorage slip. So no connection is perfect. If this shear wall is going to start tipping over, it's typically going to move a little bit before it actually fully engages the hold down anchor. So that's where that anchorage slip comes in. This typically would be specified by a manufacturer. So if I go back here to the hold down anchor, the rightmost column, it has deflection at highest allowable load. And you can see it's on the order of 1/8 of an inch or something like that. Okay, so we've done all this. We've looked at how we design shear walls. Now let's try to do it in ClearCalcs. And going back to our little story here, we've got our pigs, and unfortunately we've got 3 new pigs and they're all lazy. So none of them want to build a brick house, so they're definitely going to need some shear walls, and we're here to help them. So what we're going to do now is we're going to look, we've got our big mean wolf blowing 8,000 pounds of wind load. And I'm going to say this is at ultimate load, and I'll explain what that means in a second when we jump into ClearCalcs. We've got some parameters here. You'll notice here our pigs are really lazy. So they want their 24-inch stud spacing because they want to have as least studs as they can. And they only want to put the sheeting on one side. And they're placing all the panels vertically because it's an 8-foot wall, and they don't want to have to deal with adding blocking to connect at the edges. So that'll make a little difference later on, which we can discuss. But that's the key criteria. And then we've got our dimensions for the house. So now let's jump into ClearCalcs. Here we go. And let's go and create a shear wall calculator. So wood shear wall. Now you'll see there's a warning. This is still a beta template. So this is the part where I will humbly ask you all to send your comments. We released this pretty recently. We're still trying it out. We're still looking for comments about how we can make it better, how we can make it more useful for you. So please, by all means, if you see something that looks off or something that you think we could do better, send it to us, and we're definitely gonna write it down and make it happen. So I'm gonna hit yes here. And we are going to load our shear wall template. So we are now in our shear wall template, and I've actually taken a image here of our design case. So if I start here, we've got the total, we're gonna go one by one. The sheeting and nail pattern, we're gonna decide at the end. Stud size and grade, we already know it's a 2x4 spruce pine fir number 1, number 2. So we can go and change this. So I'm just going to type 2x4 SPF number 1, number 2. We're going to pick that. What do we have next? Sheeting on one side, 24-inch stud spacing. So I'm going to change this, 24, and we can leave this like that. Okay, the total wall length. Let's look here. So 4 plus 6 plus 6 plus 4 plus 3, that's 23 feet. And the story height, we have it at 8 feet. 8 here. Next, we're going to enter our actual openings. So we've got a window here with our 3 friends and a door. So let's start by this. So distance from the left, 4 feet, and then 6 feet wide. And you'll notice we don't have any kind of vertical dimensions here. The reason we don't have these specified is actually it doesn't quite matter when we're using the segmented wall approach. Whichever dimension you want, as soon as there's an opening, it doesn't actually affect the strength calculations. The reason we have it there is when you are making your report or showing to the client their design, typically like to see where their windows are at or something like that, so you can enter it to show it in the image. So here we're going to say 3 feet and a 4-foot high window. So we can see we've got our window here, and then we've also got our door. So 4 plus 6 plus 6. We can just type that manually. So 4 plus 6 plus 6, so 16 feet. Opening width was 4 feet, and then this one's at the ground, so 0. It'll be a 7-foot door. So we can see on the right now, we've got our window and our door. So our openings are inserted. Going down now, we've got our wall self-weight. We're gonna leave this at 10 pounds per square foot. If you've got a really heavy wall or some really heavy paneling on the outside or something like that, you might wanna change that. For now, we're just going to leave this at 10 pounds per square feet. And we're also going to look at the loads at the top of wall. So what did we have here? Let's look at the dead and snow loads. We had 100 pounds per linear foot dead load and 200 pounds per linear foot snow load. So these are loads that are coming in from the roof, sitting on top of the shear wall. And the dead load in particular is going to be helpful for us because it helps us prevent the whole thing from tipping over, because it's kind of keeping it down to the ground. And then the snow load, that one becomes important because our end cords at the end are going to be taking some of that snow load. One thing I'll note here is that we're not actually doing the design of the stud wall itself. So it might be actually that 24-inch studs, or sorry, 2x4 studs at 24 inches isn't enough to support these loads. We're not checking this in this calculator. For that, you can use our stud wall calculator, which will do that job. Here, we're only looking at the lateral loads. So going down, I'm going to put in the 100 pounds per linear foot dead load, 200 pounds per linear foot snow load, and looking here, we've got our 8,000 pound ultimate wind load. Now, the reason we say ultimate here, whoops, there we go, is if you look on the diagram here, and I can perhaps zoom in a little bit, we've got our 0.6 W 4,800 pounds. So we're actually multiplying this wind load by 0.6, and we're doing this for you in ClearCalcs. The reason we do that is because the latest design standards are mostly based with wind loads being at the LRFD level already. So if you were designing this using LRFD, your load factor here would be 1.0. But to take this down to the ASD load level, we multiply it by 0.6. So it's really important here that we enter the ultimate wind load. This would typically be calculated per ASCE 7 or per the International Building Code, either method. But the important part here is that we're using the ultimate wind level. We're not factoring it down. ClearCalcs will take care of that for us. So, zooming out again, or actually I can stay zoomed in. Temperature range, we're just going to leave this. If there's snow on the ground, it's probably going to be less than 100 degrees Fahrenheit, so we're going to leave that as is. So now we've input all our design parameters. First thing we can look at here is what's failing. Our wind shear allowable is failing. We're at 127% utilization, and our cord compression is also failing. We're at 162%. Luckily, our cord tension here is okay at 60%, but wind can blow in either direction, so we have to account for both scenarios being in compression. So that's why we're going to go here and say number of stud plies in cord. Right now we're at 1. If we put 2, woohoo, everything's okay. We're passing with our compression cord, and our cord tension is still good. So all we did here is instead of 1 2x4 at the end of our panels, we've now got 2 2x4. So each panel, so everywhere between the openings, will have 2 2x4s on each side. The last thing to do now is to look at the sheathing and the nail pattern. So here we're going to click select, and we're going to open this. And here we've got a bit of a big database. Now, we can use our knowledge of the pigs to make our lives a little easier. We know that they're really lazy, so they probably don't want to nail very often. So they're probably going to want to have the highest nail spacing possible. And they also don't want to lift heavy stuff, so they're probably going to want the highest strength sheathing. So I can come here in the sheathing grade and specify structural 1, which is higher strength sheathing than the typical strength. And now I can just scroll down. I can see, okay, this one passes, but I need my nails to be at every 3 inches, right? 6D nails at 3 inches. Let's see if we might be able to have a higher nail spacing. So if I scroll down now, I can see 7 16-inch, 8D at 6 inch. We're still not passing. 15 30 seconds, 8D at 6 inches. No, but if we use 10D nails, so 10 penny nails, we're good. So we're going to pick that. Now, our little pigs are happy because they don't have to nail very often. They're using the best grade plywood, and they can resist the loads from our wolf. We can see we're at 90%. So the big mean wolf can blow all he wants, and our pigs are going to be happy in their little house. With that, I mentioned one thing earlier about the aspect ratio. So if we look at the panels here, we've got 1, 2, and 3 panels. And we can see the panel the most on the right is very narrow. So let's look at the impact that has on its capacity. So I'm going to go now into our detailed view that shows all the calculations for our shear wall. And I'm going to go in the shear capacity section. So one thing you'll notice here is the specific gravity adjustment factor. So because we're using spruce, pine, fir, it has a lower density than say southern pine or Douglas fir. So we actually reduce the capacity of our shear walls a little bit. And that's to account for the nails being a little easier to pull out of the wood than say in Douglas fir or southern pine. Then we can look at the nominal shear capacity per panel. And this is where it gets interesting. We've got our aspect ratio factor. So if I zoom in a little bit, the ARF, you can see here our aspect ratio, H over B, 2.67, which is greater than 2. If we go back to the presentation here, we said if the panel aspect ratio is greater than 2, we have to adjust for that. So now going back to Clear Calcs, we see we're greater than 2. And so we can see we actually lose 25% of our shear capacity because that aspect ratio is a little high. And so you can see, whereas the other panels have 874 pounds per linear foot nominal shear capacity, the third panel only has 656. So that's to basically really highlight that if you have really narrow panels, it's going to affect the capacity of your shear walls. With that said, I think that we've basically concluded our example here. We started by setting our stud spacing, our stud size and grade, which we'll say was determined by our actual gravity load design and making sure that the wall itself was okay for gravity loads. We've set our number of stud plies based on the allowable cord compression and tension. We've also made sure that our largest hole size is adequate. And then we've set our wall length, story height, and wall openings based on the actual geometry. And as I mentioned, the height from floor to bottom of opening and the height of opening. So the vertical dimensions of the openings don't matter really in terms of the segmented wall approach. So that's why we're kind of okay with not having very accurate dimensions here. If you are using other methods, however, this could have a significant impact on capacity. So do be mindful of that. Otherwise, we've got one side sheeting. Our panel edges are fully fastened and blocked. And our nail spacing in the field of panel, so that's the nails basically elsewhere than at the edges, 12 inches, which is the maximum spacing. Again, we've got lazy pigs, so they want to nail as little as they have to. And then we've set in our loads. So we've got our dead load that's going to help counteract the overturning, our snow load that's going to increase the loads in the compressive cords. And then we've got our ultimate wind shear load, which is the LRFD wind shear load of 8,000 pounds that then gets factored down to 0.6. And we've got no seismic loads in this case. And based on that, we're then able to go and select our 15-30 seconds structural 1 OSB or plywood sheathing with 6-inch spacing using 10 penny nails. So that's our design example. Going back now to our presentation, I'm just gonna have a quick conclusion. So basically what we discussed today, wood shear walls, they are a very efficient way to prevent a building from basically falling sideways. There are other methods. Wood shear walls are one that are very common in residential small houses or something like that, but there are other methods. Key components that we want to look at when we're talking about wood shear walls are the sheathing, nails, cords, and the anchors. And actually, you know what, that reminds me, going back to our design example, the one thing that you'll notice we didn't look at was the hold down anchors or the sill plate anchors. The reason we didn't look at this is because this will typically be designed as part of going through a catalog as I showed and checking what hold down actually works. So what we can do, however, is we can look what's the maximum cord tension load. In this case, it's 2,920 pounds. So we could then go into, say, a Simpson Strong Tie catalog and see which hold down actually works to support to hold that load. So that's what we would typically do. Eventually, send it in the comments if you think it would be useful to kind of have that catalog in ClearCalcs. That's something we're looking at doing. There's different possibilities, but for now, it's just a matter of taking this load and looking what matches in the catalog and using the appropriate hold down. Okay, going back to our PowerPoint. We've got our happy pig here because he's got a safe house and it's efficient and he gets to be lazy and be happy. The other thing, ClearCalcs, we've just released our shear wall calculator. It's still in beta mode as we discussed. So please, 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 please send us your feedback. Tell us how we can improve it, make it save you more hours out of your days and make it more valuable. We love this kind of stuff and it makes us very happy to be able to make your day better. So please, please, please share with us. With that, I'd like to say thank you, and I think we'll have a bit of time here to answer some questions if you have any. I don't know if Connor, you want to come back on?
Yep, jumping in. Thanks, Laurent. Great presentation. I got quite a few questions throughout the presentations, and then now the questions are kind of blowing up, which is awesome to see. So what I'm going to do is start with the one just kind of top down that I got throughout the presentation. And then anybody that's asking a question right now, of course, we'll do our best to get to it in the next 19 minutes. But if not, what we'll do is send through responses and make sure all of them are answered kind of after the webinar when we send a follow-up email to you all. So first question I got from Josh Van towards the beginning, he was just curious and I think just wanted some confirmation as to why we assume that lateral load, even during our example as well, is only at the top of our shear wall.
That's an awesome question. And so the reality is, especially when we're dealing with seismic loads, it might not actually be at the top of the wall. If we're thinking about, let's look here at this example here. So if we're thinking about the weight of the wall itself, typically the force will be applied kind of centered on the center of mass of the wall. But that said, when we're looking at shear walls, they are resisting the load parallel to them. So you have to think about, say, if I've got this big house, and then I'm trying to make hand gestures here. I've got this big house, and then I've got the wind pushing on a wall. That wall goes through the floor or the diaphragm and goes into the shear walls. And the floor is typically kind of sitting on top of the walls. And that's why we'll assume that this load kind of gets carried to the top of the shear wall. I hope that I made it clear. You're making me regret not having kind of a top-down view of a shear wall now. Maybe we can kind of see it here where if the wind goes from left to right in this case, it's going to be hitting the walls that are going up, down, and then getting transmitted by the floor into the walls that are going left to right.
Yeah, and then Josh, feel free to shoot me an email if you do have additional questions on that. And then if I see a few more questions in the chat here regarding that and maybe some further clarification, we'll be happy to either create a video or article or any sort of help content that'll make sure we're all on the same page.
Absolutely.
So I did get the question/request from quite a few people: Kayla, Rudy, David, Donovan, and I'm sure one or two more, but those were the only few I could quickly type out here. Regarding any plans down the line of the perforated or FTAO shear wall design methods.
So the short answer is if you're going to use it, absolutely, we'll want to have it. What I would love to hear is what are the typical kind of conditions that you would pick one method over the other. We'd absolutely love to look at different ways we can make your life easier and make more efficient shear walls. So the short answer is yes. What I would ask of all of you is tell us more about when you're using perforated or FTAO methods, and let's see what we can do to make your life easier.
Awesome, and thank you all for that request. As you guys all know, everything we add is purely based off user suggestions, feedback, user input. So the fact that we just got at least 4 or 5 of those throughout this webinar definitely makes it so it's going to be added to that roadmap. Kind of dovetailing on, Kayla was one of those that she was actually the first one that asked about the perforated and FTAO. She had another question. She asked, does the calculation show the overturning moment and the resistive moment of the shear wall?
Great question. So if I go into calculation and into detailed mode, the philosophy here at ClearCalcs is that we want to be completely transparent about this. So if I go into my chord loads section here, you can see I have my header reactions, which are basically controlled by the snow load, the dead load on top of the ceiling that are resisting by the headers and is going into the chords that kind of act as jack studs at the same time. And then you can see here, resisting moment, right? So we've got a resisting moment in panel 1, 2, and 3. So 1440, 4440, and 810 pound-feet. And you can also, if you click here, you can see directly the equations that we've used to calculate that restoring moment. So it's all there for you. And then if we think about the overturning moment, similarly, we can see wind overturning moment, 12,500, 18,000. And again, you can see here, so it's the wind shear times the story height. And that tells us our overturning moment. So I hope that answers your question. If you think there's a step missing here or that we can be a bit more transparent about, let us know and we'll see what we can do.
Yes, thank you for that question, Kayla. And then just to kind of circle back on the perforated and FTAO shear wall methods, just to kind of have it in our video recording and make sure everyone who's watching is on the same page. Thanks, Aaron, Kayla, and Garrett for sending through a few common scenarios where they use this. Of course, we'll take note of these, but for everybody's reference, Aaron mentioned usually perforated, or he would use perforated just in general if it were available in ClearCalcs. Kayla mentioned FTAO typically around garages. And then Garrett mentioned they'll typically do the more advanced methods. I'm assuming the perforated and FTAO and commercial. And then the residential is more segmented. So just to close that one off. Thank you guys all for sending through your comments there. All right, jumping through to the next one. So Randy Katz out of Oregon, he had just wanted to mention and appreciate this note here, Randy. This helps internally. That in Central Oregon, the wind loads are typically higher than the seismic for shear walls. He just mentioned that when you mentioned sometimes or most of the time wind loads potentially are negligible, or I forget what word was used, to be honest.
I think perhaps when we were looking at the deflections and we mentioned that sometimes the wind loads will be ignored when looking at deflection. A really interesting point about sometimes wind loads govern over seismic loads. One thing to be aware of, however, is when you're designing in high seismic categories, there may be some specific detailing requirements to achieve, say, ductility or more resiliency in your building, that even if your wind loads govern, you still need to have those detailing requirements. So just a side note, I just want to make sure that we mention that.
Yeah, appreciate that background, Laurent, and thanks again for that comment, Randy. Another question from Randy that I'd mentioned I'd bring it up during the Q&A is we were talking about the wind loads here in the deflection slide, and then when we went into our actual example where we were saving those pigs, we went straight to the 8,000 pound ultimate load. So he was just curious, you know, where was that wind load determined? I know you mentioned we would be using, or they would use ASCE 7 most of the time. Just curious if you could comment on that.
Absolutely. So now jumping into a bit of a fantasy land here where our pigs are only scared of the wolf and want to survive. The assumption here was they didn't care about the deflection. Maybe that's fantasy land. Obviously, your real customers are probably not actual pigs, and they probably do care about the deflection. So the short answer is the design codes in general do not provide limits on wind deflection, and they don't necessarily provide service loads for wind. Now, this is evolving, this is changing. There are now, say, service load combinations that include wind. I think typically we'll take 0.45 times the ultimate wind load. So in this case, our service wind load that we would check our deflection under would be 0.45 times 8,000, which is a little under 4,000 pounds. The biggest reason we don't have that in ClearCalcs as of yet is basically we put in our shear wall calculator, and we're actually looking for feedback on how might we implement deflection so that it's useful for you. What do you typically check in deflection? What are the specific projects where you would look at it? Are there projects where you don't? So actually, I'll take this opportunity to ask another request of everyone here. If you can tell us when you look at deflection in shear walls, when you might not, if there are specific considerations that you look at with that, we would love to hear them, and we'll make sure that we can have those deflection checks as useful as possible for you.
Yeah, thanks for that, Laurent. And kind of on that same topic, just because I got a few of these questions, so I just wanted to clarify. You mentioned the difference between the ASD and LRFD, and how in ClearCalcs we're automatically doing that 0.6 times the ultimate. So Randy had a question, and then Donovan had a question as well. So one, just to kind of reiterate and confirm where that 4,800 came from when we started with the 8,000, and then once you're done that, one question at a time, then I'll ask the next question.
Absolutely. So the wind load here comes from the load combinations, right? So we enter the ultimate wind shear load. If we look at the load combination, I'll zoom here. Maybe I zoomed in too much, but 0.6 times the applied wind. That is specified, either that's in the International Building Code or an ASCE 7. This is an ASD based calculator. So in either the International Building Code or ASCE 7 or your local building code, they will typically have load combinations to be used in ASD design, and that's where that 0.6 would come from. So they would say your wind load, in the building code, it would say your wind load is defined as such, and then it'll give you, the big formula and the wind load map, the wind speed map that you calculate that. When you calculate that number, if you want to use it for design in ASD, multiply it by 0.6. And that's what we're doing here. So we're basically saying you have to calculate that number, which again, ClearCalcs can help you with that. That's a separate webinar. But you have to calculate that number, and then we'll take care of the 0.6 so that you can meet your building code requirements.
So thanks, Laurent, and kind of along the same lines there. So Donovan had a question basically. So if he has a wind program or he's doing his wind calcs and it's outputting basic ASD values, he asked, do I need to factor them up to input them into ClearCalcs?
Yes, that's an awesome question. Yes, the answer is yes. So if your program is giving you ASD values, you do need to factor these up, because otherwise those factored ASD values basically already have that 0.6 in them. So you absolutely will want to remove that 0.6 so that ClearCalcs can put it on there again. A little counterintuitive, but that's a critical component here, and that's why we take the ultimate wind load. So the way you can do that in ClearCalcs is really easy. You just do divide by 0.6, and we've now taken care of it. So if you look on our diagram here, we've got our 8,000 pounds that's showing up now.
All right, thanks, Laurent. Another question here. Sorry, I'm just firing them at you, Laurent, but thank you everybody for all your questions.
Awesome.
Keeping you on your toes. So David Bertel asked, all the questions coming from Oregon. Thank you all. Or I guess, David, you might be in Washington, I believe. Jim's in Oregon. But anyways, do you guys, or do we have the ability to use, for example, a 4x6 post instead of a 1.5-inch wide stud for the cord?
Great question. So here, I'm sorry, I just erased this by accident. The short answer is kind of a yes and no here. We don't currently have a way to specify different cords than the rest of your studs. That said, and I'm going to say this with a big caveat that you really need to make sure that for your project this applies. The stud size and grade has very little influence, if any, on the actual shear capacity of your wall It's more of a detailing requirement in that your stud needs to be greater than a certain size to meet the code requirements. So if you went in here and say picked a 4x4 post, let's go to Douglas fir this time. You will get the allowable cord tension and the allowable cord compression. That's in this case, we've only got one. You would get the appropriate values here. If you want to be sure, for now, and I'm going to take this kind of as a suggestion for us. For now, you could create two sheets, and one of them would have, say, your end post, and you can say this is for checking the cords, and then the other one is for checking the sheathing. If this is something that's common, what I would ask is write to us about it. This is all great ideas. We'd be happy to have different inputs for the studs and then the end posts.
All right, thanks, Laurent. Question from David Hordequin, and thanks for joining, Dave. Good to talk to you.
Hi, David.
He asked, and I think this is a question most people have, and I know you touched on it, but I think it's important to just reiterate and confirm. So when we finish our shear wall designing clear calcs, and now it's time to select potentially Simpson strong tie anchors or hold downs. So where are the values in clear calcs that we then kind of translate over into their tables to select what's going to work?
Great question, right? So why don't we do it together right now if you guys want. So if I go at Simpson, whoops, it's gonna give me the, oh, my computer's being Simpson, hold down catalog. And I go here and hold downs, let's just pick one at random. And if I go look at this table here, it's going to have allowable tension loads. And then this is the, say, 840, 2145. These are our loads, right?
Can you just zoom in a little bit on that,
Yep.
Laurent? Thanks.
Certainly. I can go look here. If I go look at there should be some footnotes somewhere. I think actually I want to do this, general information. And here is where I would see. To obtain LRFD values, multiply ASD seismic loads. So basically what they're saying, and I apologize, I don't have the exact clause with me here. These design values are based on the allowable stress design load combinations. So what that means in practice for clear calcs is you can literally just go and take your cord tension load. Now, again, with the caveat that if you've got a weird design scenario or something like that, this number might change, but in general, you can just go and take your maximum cord tension load. So in this case, 2,920 pounds. And you can go into the catalog and see, for instance, okay, HDU2, SDS 2.5, 3,075. That's it, I'm good. I hope that
Perfect.
clarifies it. And then again, there's the big caveat here that, you know, specific design scenarios might have specific conditions that you want to account for, but in general, that would be the method.
And for everybody watching and kind of viewing here live today, I hope you guys have noticed we do have our wood connector calculator out, I think a month or two ago, where basically you can select from the Simpson strong tie hangers. And as you guys know, we just continue to put out more and more content. So the not sure the word I'm looking for, but eventually we will have, as long as it's suggested and recommended a ton of times, we will have the ability to actually select your anchor within Clear Calcs, very similar to the hanger as well.
I'm not too sure, my computer's being really slow here, but normally, there you go. There's the wood connectors. So you would be able to say, yeah, your joist size and grade, and then your connector based on a Simpson catalog. If you've got other manufacturers' catalogs that you want to see in there, you know, obviously message us. And the cool thing, I'll just throw that in there while we're here, you can link this to your joist calculations directly and import the loads and the joist sizes to make sure your connectors are compatible.
Perfect. Quick little plug for the for the connections calculator. Looking at the time here, we've got less than a minute left, and I know there's a lot of questions, comments in here. What we will do, Laurent and I will meet later this week, and we'll just kind of touch on every question that we didn't answer and make sure that everybody who's viewing has access and can see all the questions that weren't answered as well as the answers, of course. And what we'll do is answer those in the form of either written responses, or I am partial to just recordings because they take me less time and typically are get a more positive response. Uh, so again, thank you guys all for coming. Apologies we weren't able to touch on every one of the questions, but look forward to seeing you guys around August 20th, whatever that Wednesday will be, give or take a few days. And thanks, Laurent, again for including the story of the three little pigs as well. Bring us back to our elementary days.
Thank you everybody for coming. It's been fun, and yeah, keep the questions coming, keep the suggestions coming. We love it, and we are here to act on them and make your life better.
Yes. Thank you all, and have a great rest of your week, rest of your Wednesday. See you guys.
Bye bye.